Welcome friends. As you know that in our previous number lecture, that is in the lecture number 12, we have completed up to the 60 number question. Okay. So in this lecture, let's start from 61 number question. Okay. So 61 number question is given that grand canonical ensemble is the collection of a large number of independent systems, and in the options there are several parameters are given. Okay. And we have to find the parameters which are remain constant in grand canonical ensemble, specially for grand canonical ensemble. What are those property, or we can say parameters? Those are mu, v and t. What is mu? Mu is the chemical potential, v is the volume of that ensemble, or we can say system, and t is the temperature of the system. Okay. And now the question comes that what is mu? That is chemical potential. You know, chemical potential is a kind of energy. What kind of energy? It is specially linked with the internal energy of the system. Okay. Let's suppose at any moment of time there are n number of particles or gas particle in a system. Okay. And after some time, some particle leave that system. Okay. And if you see that there is a now there is a change in internal energy of the initial and the final state. And this initial final state internal change in internal energy is known as chemical potential. Okay. And the v is, as you know, this is the volume, and t is the temperature. Now uh, to give some better understanding, I have mentioned here the properties of the walls that are present between the ensembles. Okay. Specially basically this this walls should have some properties. These are not ordinary walls, as you know. Okay. The walls have permeable property. It should be rigid and it should be diaphragmic. What is mean by permeable? Permeable means particle can move from one ensemble to another ensemble. Okay. And what is rigid? That means the walls are rigid, that are not movable. You imagine, if the walls are movable, then the volume that is remaining constant, the parameter volume which is kept remain constant in grand canonical ensemble, will not remain constant because the walls are moving. So if walls are moving, then how the volume of any particular ensemble will remain constant? So it should be rigid. Okay. And what is diathermic? Diatherm means the temperature of that system will remain constant. How can the temperature of a ensemble remain constant? Only if that ensemble exchange heat with its surrounding ensemble, then can any ensemble can remain in a constant temperature. Okay. With its surrounding. Okay. So now coming to the 62 number question, it is given that the partition function of a perfect monatomic gas in canonical ensemble is, where this the lambda is given as s by 2 pi m kVt to the power half, and this lambda is nothing but the de Broglie thermal wavelength, and we have to find the partition function. Okay. So if you see the solution, before doing this question, you should have some background knowledge about the perfect monatomic gas. What is mean by perfect monatomic gas? Perfect monatomic gas means they are ideal and they have no interaction between them. So if they have no interaction between them, that means what? They are free from each other. If a gas is not applying any kind of force with its surrounding, then what is meant by that? That means it is free. Okay. So if a particle is free, what kind of energy it possesses? It possesses only kinetic energy. There is no potential energy. Okay. And here is the formula of the partition function for n particle. Okay. And this q1 is the partition function of a single particle, and the formula is 1 by h to the power f double integration e to the power beta e del q to the power f and dp to the power f. What is f? F is the degrees of freedom. So what we do here is we first find the partition function of a single particle, then we can put that formula here. So what you do, let's find out the value of q1. Now for a single particle, what is the value of f? That is the degree of freedom. It is 3 because it can move only in 3 directions. You should remember that, you should remind in mind that we are not considering this whole process at a high temperature. There is a temperature limit, okay, here. So actually in high temperature there may be the vibrational degrees of freedom may arise, so we are neglecting here. That means we are taking the case of low temperature, low temperature. So if you put here the value f equal to 3, then you do the calculation, then you will get that integration of dq3. This is nothing but v, that means the volume of that ensemble. dq3, that means there are 3 differential terms that are multiplied here, dx, dy, dz. That this is, and there is an integration, that means this is nothing but a volume term. And just now we have to find the value of this quantity. Okay, this is, if you calculate this from 0 to infinity, okay, and if you apply the gamma function, that is 0 to infinity x to the power m e to the power alpha x to the power n dp, sorry, this is not dp, this is dx. Okay, I have wrongly write here. So this is 1 by n, this n. Okay, this is the formula. Okay, this is the formula. If you apply this formula here and you do the calculation, you will get q1, that is the partition function of a single particle, is v, that is volume, whole under 2 pi m kbt by h square to the power 3 by 2. And this you can also see this formula. These are nothing but, if you have this gamma function in this term like z plus 1, then we can convert it like z gamma of z like this, and this beta is nothing but the 1 by kbt. Okay, you just put here and you get this answer for a single particle partition function. Okay, so lambda th is h by 2m kbt to the power half. Okay, now you make lambda th to the power 3 and you will get this. Okay, you will get this, and now you have to convert this q1, that is the partition function of a single particle, in terms of v by lambda th, because if you see the options are in this form. Okay, n, v and lambda th or lambda. Okay, so you have to convert it. Now this is the conversion. If you convert it, you see I have not elaborately shown you. Okay, if you convert it, q1 will be v by lambda to th to the power 3. Okay, for this is for a single particle. Now you have to put this formula in for n particle. For n particle, q1 is q1 to the power n by n factorial. You put this formula, you will get this. That is the option number A. Okay, this is the option number A. Now coming to the 63 number question. 63 number question is asked to find the ratio of most probable velocity to the RMS velocity, root mean square velocity. Okay, and what is this most probable velocity? This is the most number of particles possessing the velocity. This is the most probable velocity. Okay, that means there is a group of particles. Okay, that means the large number of particles the large number of particles corresponding velocity is the most probable velocity. Okay, so let's suppose there are 10 particles, and among the 10 particles, 5 particles have velocity, let's suppose 300 meter per second, and three particles have speed have a 500 meter per second, and two particles have a speed 100 meter per second. Then what is the most probable velocity? Most probable velocity is 300 meter per second, like this. Okay, now if you see that this is given for to find for a molecule. Okay, actually if it is mentioned to find this most probable and RMS velocity for different molecules, then it will be difficult. Okay, okay, as it is mentioned that for a particular for a same molecule, then it is easy, we can make the ratio. Okay, because if you see the solution, there is a mass term here. You see, this is the mass term. Okay, so for any particle, for any molecule and any gas particle, the mass may be different. So that's why this most probable and VRMS can be different. So that's why I'm talking like this. Okay, so you just you know that the VRMS and VMP, that is the most probable velocity. This is VMP will be root over of 2 kVt by m, and VRMS is 3 kVt by m to the power half. Okay, you make the ratio. This is easy question. Okay, and you will get a root over of 2 by 3, and this is nothing but a 0.81. Okay, so now coming to the 64 number question. This is again a simple question. You just know the essence of this Gibbs paradox. Why it is arised? Why it is arised? Actually, this is arised because of the consideration that we are considering in previous, before Gibbs paradox. We have considered that the gas particle are distinguishable. That means we can distinguish them separately, that this is a particle, this is B particle, or this is one particle number 1, this is particle number 2, and this is particle number 3. But actually after the Gibbs paradox has arisen, we consider that no, these particles are not distinguishable, they are indistinguishable. So that's why the indistinguishability nature is comes into this picture. So that's why the whole Gibbs paradox is then removed. Okay, this is the essence, and this is the so that's why option D is the correct one. Okay, this term, this is the additional term. Okay, so now coming to 65 number question, and the last question of this lecture, and it is asked to find the Boolean expression for NOR get. Okay, NOR get is a universal get, and we have to find the Boolean expression. Okay, what is the Boolean expression? You see, this is the easy question from digital electronics. You see, this is actually the from this to this is a OR get, and if you make it, if you apply a NOT get, you will get a NOR get. Okay, actually this is OR plus NOT is equal to NOR get. Okay, so if you give two input A and B to a OR get, you will get A plus B, and after that if you get a NOT get, you will get A plus B to the power 2 bar. Okay, A plus B bar. Okay, so that's why if you see this is option B is the correct one. Okay, so hope you got the answers of all these questions from starting from 61 to 65. Okay, so thanks.